So today we're going to be talking about neural networks. Some people might know it as like kind of the cool part of AI or whatever, and they're like essentially the basis behind modern machine learning. Everything that we've discussed so far is based very, very much in statistics, but this is more. I mean, this is technically statistics too, but it's kind of like machine learning all on its own. So, as a quick question, who has seen something like this before? Kind of just like yeah, you've seen something like this before. Yes? Great. Okay, so this is essentially what we're going to be talking about, and this may just look like a whole bunch of circles and lines, which it is at this point. But this is what we're going to. This is what's known as a multi-layer perceptron. Most people just call it neural networks at this point. So essentially, the way it goes is that data flows in here, and it will. There's a hidden layer here. We'll do some linear algebra, and then it'll go to the output. And then the output will compare it to the actual label, the actual, the true value, and then it will update itself back and just keep going back. And the most important part are these weights here. And those are things that are going to get updated. Because what we're going to be doing is similar to. Does everybody remember this from like 8th grade? Like the equation of a slope, or the equation of a line. So y, our output, equals m, which is going to be in this case our weights, x, which is going to be our input, plus b, which is in this case it's going to be called bias. For those of you who have taken previous classes of mine, this might seem a little basic, but I'm going to go over it. We're also going to use it in a very much higher level way as opposed to doing it all from scratch as we did before. Great. So a little bit more basis behind this. Also, always remember to ask questions. A little more basis behind this is we have y equals b, and then with each. I really should not do is that. And with each layer, with each additional set of what we're going to call neurons, the circles, we can add more m, x, y, 1, 2, plus m, 2, x, 2, et cetera, et cetera, et cetera. So we're just going to keep adding them all together. That make sense? Okay. So let's step briefly into the code.
I'm sorry, quick question. Is it really adding or multiplying in a sense?
In this case, we're going to be adding, but there's a different, okay, that's actually the question. So between here and here, we're going to have what are known as activation functions. In this case, it's going to be ReLU, rectified linear unit, which is a function that's going to mx plus b, and then we're going to pass this through a new function, which the equation for that is going. The graph that's going to look like this, and then x where y is greater than 0, else. So it's called a rectified linear unit, and I'm not sure what the name stems from exactly, but the idea is that as long as we, when we go here, we're essentially going to multiply it by x again. We're going to multiply it by itself, and we're going to send it through to the next layer. There are many, many activation functions. Another popular one is called the sigmoid activation function, which looks a little something like this. This should be 0.5. We're going to we're essentially going to multiply our output based on where our based on what we predict, and that's going to add a layer, another layer of non-linearity to it. Because if all we had was this, and we just kept going, it would just be a straight line essentially. So by adding another layer of this non-linearity, it'll add an additional layer of complexity to it. Does that make sense? Okay. I don't remember the equation for sigmoid off the top of my head, so I'm sorry for that. But yeah. So what's going to happen then is we're going to pass everything through the mx plus b, and we're going to get the output. We're going to compare it, and we're going to generate a loss function, or just how different, essentially how much different the true value is compared to the predicted value. And with that loss function, we're going to take the derivative of that loss function, or the measure of the distance that it is wrong, essentially, and we're going to update these weights again. And we're going to take the derivative of what was here, and we're going to essentially just keep going back. The chain rule from calculus, if you are familiar with calculus, we're just going to keep multiplying the derivatives based on the entire function. Also, at the very, very bottom of this notebook, I made a little poll, and it's essentially like for next week what we can do. I was going to get to this at the end, but this is kind of similar to what we're talking about right now. At the very bottom of this notebook, there's a link for a straw poll, which is just like, it's a poll, and it's what we're going. I'm letting you guys choose what we're going to cover next week, and we can either go a lot more into the math behind all of this. We can also go to a much more popular framework for doing this kind of stuff, or we can learn something completely different altogether. Maybe wait till the very, very end in order to vote, but if you want to learn more about all of this, we can teach it next class, because it might essentially take an entire class to cover that kind of stuff. If that makes sense. Okay. Are there any other questions regarding this? No? Okay, cool. So we're going to do code again, just like, the reason we're here. So here are all of our imports, pandas to deal with data, NumPy to actually be able to manipulate numbers and everything else. We're going to grab our data sets from sklearn again, PLT in order to make it look beautiful, pre-processing to pre-process our data, Seaborn as SNS for also making it look beautiful, train test split, which will split our data between the training and testing. We're just using this, the Fusion matrix and the classification report, and that's going to be to actually get statistics on our models. Standard scaler, the scaling our data, MLP classifier, MLP regressor. These are going to be our actual models. As we said before, this is multi-layer perceptron classifier and multi-layer perceptron regressor, and sklearn metrics. So that's great. We're going to actually run some code. Oh, I also put the documentation for the scikit-learn neural networks up here. So if you guys want to check that out, you can see all of the different type parameters to play with, and essentially all the information about them. So we're going to start running this. We're going to So what I wanted to do was I wanted to take our multi-layer perceptrons and compare them to our previous regression method, or our previous our previous regression methods, which is going to just see how they compare. In order to do this, I'm using the exact same IRIS dataset and the Boston housing dataset. So we're going to grab the IRIS dataset from here, which is just classifying flowers. We're going to split all of it with 20% of it going to the testing dataset. And then we want to scale it, as we had done previously. And this is just going to put it into a more usable format in order for us to, just so we don't affect the network too much. Because networks, the neural networks, they're pretty finicky. If one of these numbers, which is going to be the input, is ridiculously high, and the other number, which is going to be the input, is ridiculously low, it's essentially, it's essentially going to learn so much from this, and it's just going to have a much harder time updating the weights in the same way. So that's why I want to keep them a little bit closer together, just in order to make it easier for us to train and easier for us to, easier for us to train.
Do we connect to the remission monitors?
Yeah, we did this. We did this for at least showed that at least. Not by fault. Okay, so great scaling. And this in this case is going to be all we need for a multi-layer perceptron classifier. The hidden layer sizes is the middle one. So if we have this, it'll just go all the way down and we'll have 10 of these. And max iteration is what's going to be known as the number of epochs, or however many times we go through our data and update. Go through our data and update. We're going to use that 1,000 times in this situation. And then we fit it. And we can see here all of the, essentially the different stuff that you can train, the different stuff that you can tune. The activation function, as mentioned before, we have ReLU. And you could also change it to sigmoid to see how that affects it. And then, all the other stuff, all the other beautiful stuff. If we were to talk about, if we were to go to the more of the mathematics behind it, you get to the alpha, you get to the beta, epsilon, et cetera, et cetera, et cetera. But for right now, I think it's just a little bit out of the scope of what we have. If we have time at the end, which at this rate we probably will, we can go more into it. So let's train. Done. Okay. Now we're going to predict based on the test, and here we can see our confusion matrix, which I would say that's pretty good. Here are all of the metrics. Here are additional metrics as well. I included the documentation here exactly about what all of these exactly mean. So yeah, the precision is just the number of true positives versus number of true false positives. What we call is essentially the opposite of that. And the F1 score is just the I'm not going to get too much into F1 score. It's not quite as important, I think. And support is the number of occurrences within however many we had in our test set. So we get about 97% accuracy on this, which we also achieved about the same with logistic regression as mentioned before. Now, the nice thing about this is we can also change this part here to change our layer sizes. So if we have 10 here, and we want to add another 10, it's extremely easy. So all I have to do is comma, 10, and then retrain. And it seems as though it got the exact they got all the exact same metrics. That's just because I guess this one example is pretty tough. But for the most part, it's able to correctly identify all 30 of these. Another interesting point to make is that with our logistic regression from before, we didn't separate into training and test set. So our 97% was from the classifications that it had already made, essentially. So it saw all the data before, but this is completely unseen data with 97% accuracy. It's the exact same thing. Any questions about that?
Just repeat that one more time.
Okay, wait, which part?
So the regression model.
So for the regression model, when we were first talking about it, we did not separate it into training and test from before. So 20% of this data, as we are splitting our data set between training and test, we're taking 80% of our training data and 20% we're taking 20% of it and setting it to the side. But we're passing all of the other 80% through the MLP classifier. So all of the other data, the other 20%, is all stuff that we have never seen, is all stuff that our model has never seen before. Where in the other case of our logistic regression, I had not done this. So we still had 80%, and that was data that it has already seen before. Does that make sense?
But we should have done that for regression model.
We should have, but that was the very first class, and I just didn't because I didn't want to try to confuse people with training and splitting. So we did not do this with the regression model, but we had done this with the support vector machines.
I can see it. Like would you choose one over the other?
What is that? What do you mean?
Like this over
Well, we're just we're kind of measuring different metrics, which is why we had 97%. One very interesting thing to note is that with this, compared to the regression model, it's a lot more computationally expensive. So if we have, this with just 10 and 10 with some very, very basic numbers, it's pretty fine. So if you can achieve the exact same thing with a regression model, I would probably suggest just using that. Because this is for graphing maybe more complex equations, like things that are maybe a little bit more complex. But you have to also trade off the complexity behind it, which will make it more computationally expensive, and it might take a much longer time than the regression model. But if you have something that a regression model just cannot do, then NLP classifier. And the great thing about the multi-layer perceptrons is that they can effectively, they're just very, very, very versatile. So when we passed our data to try to do the regression into our our linear regression into our logistic regression, it kind of just broke and had like a 10% score, right? Do you remember that?
The Boston or
when we passed the Boston one to the logistic regression, and in return it had like 10% score.
Yeah.
That's very, very bad. With multi-layer perceptrons, it may seem very, very similar in the sense where we essentially just have to change the word classifier to regressor. But it's the fact that we're essentially making the model more complex, and we're just changing one or two things, and that's going to be able to give us, it'll be able to achieve many, many tasks for us. So it all depends on, a lot of it depends on these activation functions. So if we're doing a classification problem, we would have the softmax activation function, which would essentially return the probability for every single, I think the equation for that is like e to the x over sum of all e to the x, I think. Someone could correct me on that. But that's essentially like the softmax equation, where we're taking the probability, and this will return a probability of what this is compared to all the other ones. However, with a regression model, we would be able to change this and essentially have nothing here, and it would just, or even like a sigmoid, and you scale it, and we would be able to actually find a much better curve. And just by changing like essentially this part of it, we would be able to change the entire function of the neural network. But I mean, obviously we would have to retrain it because they're trained for completely different tasks. But in this case, what this will essentially look like is, since we have, I believe, I should have looked at data, but I figured it's good already looked at before, but I didn't have to the case, I guess. So we effectively have 0, 1, and 2 classification. Okay. So what this will look like is we'll have 0, 0, 1, 2, and we'll say 0, 1, 2. Okay. And just by using this softmax equation, which we're telling it to do that based on the classifier, we're going to be able to determine the probability behind this. And then from here, we're just going to be able to take the maximum probability, and then we're going to be able to make a prediction based on that. Does that make sense? Does anybody else have any questions, or did I just confuse many more people than I? I know somebody has to.
So the output of this is like a probability.
Yeah, exactly. The output of this is not 0, 1, or 2. It's going to be a probability of, this is going to be like 97%. This is going to be 2, and this is going to be 1. Or I guess like 0.92, 0.02, 0.01. And that's going to give us. Then we're going to take, okay, so we have 97% here, then that's going to be the output. It's going to be 0. Because at this point, we had already encoded all of our data as 0, 1s, and 2s as opposed to the actual classification for it. Because of this return xy. Since we did that, we're able to actually look at it. It's just going to give us the x and the y in their purest form as opposed to having to deal with all of the data that's behind it. Or like all like the metadata about like the sepal length, the stem length, leaves, shape, or whatever. And it's just going to give us the actual numbers. We can actually look at the essentially what it's going to return, if we just do that, it's very, very ugly. But this is essentially all the data we're passing through our multi-layer perceptron, and because scikit-learn is so nice to us, it will automatically adapt itself to, instead of having 2 here, it'll say we have 5 for each data point. And then each of these 0, 1s, and 2s are going to be paired up with one of this as the label. Does that make sense? Any questions? Yes.
The scikit language you choose regularization.
I believe so. I'm not 100% sure. I don't use scikit-learn super regularly, so I have to check on that. But I think I want to say yes, because Don said when I was looking at this earlier that it said L2. But I might be wrong. I would have to check on that.
Okay, thank you.
Okay. So we got through all that, and we got our confusion matrix as we have seen before. And now we're going to do the Boston data set, which was our linear regression example. So we're going to do all of the exact same things. So we're going to load Boston into that, and x, y, which is going to be our inputs. Going to split them up with training and testing. We're going to scale them, of course. And then, again, this is just going to be our regression model again. This is going to be the regression as opposed to the classifier. So it's going to let us essentially grab a function as opposed to determining the softmax output of all of these things. This is going to actually try to predict a number as opposed to the probability. Okay, and if we run that, and we can see the score, it's at 72%, which admittedly is not super great. Because with the other regression model, we got 92%. So what we can do with this is we can change the size of the layers. We can change the number of the layers, and we can effectively add this to make it look more like this. We're going to add different layers of 10 each. And it doesn't have to be 10. It can be any number you want, your favorite number, your least favorite number. We're going to fit that, and well, it's actually about the same. So we can also play around with it. Okay, well I was getting like 93% earlier. So maybe in this case, a multi-layer perceptron would probably be a little bit overkill in that way, just because the linear regression model, what we're trying to predict is the actual linearity. We're trying to predict a number. In this case, it's a very linear number. The Boston Housing data set outlines the prices of housing based on certain features. So I guess with just with the regression model, this would be, it would suffice just as much. It would suffice fine. We also can change the maximum number of iterations, which if we check here, actually that a little bit. But what this would do is it would effectively make it train for much longer, which is again with a trade-off between computational complexity versus the it's a trade-off between computational complexity versus the precision. And another thing about the maximum number of iterations is that we're risking overfitting our model. So if we have our data set that looks like this, and this is going to be x1, x2, which will be our number of features, which will be our features, and then an ideal regression model would predict it to like this, which is pretty good. It's a pretty accurate representation of our data. However, if we do the maximum number of iterations as a very high number, and we have a sufficiently complex enough number of layers, it would essentially turn to something that's more like this, where it would hit every single data point, but it would be very bad at it would just be very bad with data that's never seen before. So if we have a model, if we have another data point that we're actually trying to make a prediction on, that would be up here maybe. Our model is already going here, so it might go here and whatever. But this would still get relatively close to it, just because it was like relatively close, so it just gives on the exact same slope as the rest of the data is. Does that make sense, everybody? Okay, so as I predicted, there were not as many questions as I hoped for today. So we're going to get into the math a little bit more behind the multi-layer perceptrons. Also, the straw poll is at the bottom. Yeah, so this was actually, I was honestly expecting everybody to have so many questions, but that's just not happening.
Well, because we're still trying to grasp what's going on.
Okay, so ask a question. Well, can you help me out? Can you help me help you understand? Yes.
How do you build intuition about designing your networks?
So intuition about designing your networks all comes from a ton of trial and error. So the easiest example probably is the layer size and the number of layers.
So this is all fully connected networks.
Yes, they're all just fully connected networks.
Right, so, but then there's all these like different people saying, oh, I put a combination layer here.
Okay, so yeah, we can talk about that a little bit. So the different types of neural networks for the bare minimum essentially are the multi-layer perceptrons, which we talked about. Okay, we have convolutional neural networks, which usually is depicted with like squares, and then an output, which actually they need to be set into a fully connected network first, and then an output. And then we also have recurrent neural networks, which can look like this. There's 100 ways to. There's 100 ways to like draw them. Some people just like make squares, connect squares. That's mainly the idea. So our multi-layer perceptron is very, very good for things like this. It's very, very good for more basic tasks. So what people do, okay, so let me so it's very, very good for basic tasks. For a convolutional network, it's probably the best thing that it's used for is image processing. Because with the convolutional neural network, you have an image here, let's say it's a little man, I'm an artist guys, and what it'll do is it'll take a little section of this, and it'll look here, and analyze what it thinks it sees here, essentially. And then it'll do the same for right here, and so on and so forth. And then that will, there are many different ways of taking these three blocks and how you want to represent them. The most popular way is to just take the maximum value of whatever pixel is right here. So in this case, like the RGB scale, so 0 to 255, this will probably be a 0. This will probably be, let's say, 255, just because we're going to pretend this is like black. And this would also probably be closer to a 0. Or you know what, for the sake of fun, let's say this is 128. Why not? And this, they would represent different numbers, and they would shapes itself into a smaller. So here we have a. Face will probably look like this, honestly. But when we have, depending on how many blocks we want to create, so here we have 3. It's just going to be a 3 by 3. If that makes sense. This part I could have done much better at the beginning, but it'll essentially look at all of the pixels in a certain square. So if this is a 1024 by 1024 pixel, and we have 3 by 3 convolution on it, it'll break it down into 3 by 3. If that makes sense. And then for a recurrent neural network, it's very, very good for data that it's on a time scale, usually. So if you want to predict stock prices, for example, you would put all the data into the recurrent neural network, and what you would find out what the next day is going to be. You would make a prediction based on that. Because this is trained on, let's say, the last 10 days, and it wants to try to predict the 11th. And then the next 10 days, that'll try to predict the 11th as well, so on and so forth. So that's what that would be good for. Now, that being said, most of the time you still need a fully connected network in there, the MLP. That's because even though we have this 3x3 matrix, we can't really do too much with a 3x3 matrix just by itself, because what you're going to see here is essentially blocks of 128, 240, 11, and so on and so forth. So it would just be very, very random numbers in convolutional output. So what we would do is we would take these and flatten them. So we would take this, concatenate, we would take these three, concatenate over here, and take these three and concatenate over here until we have a 1 by 9 matrix, 1 by 9 array. And we would pass those 9 into this multi-layer perceptron. We are so far off this main topic that I very, very much believe that nobody has any other questions you're going to say. I don't know. One of you do. Anyway, so we'll pass these into a fully connected network, and by using one of the different activation functions, we'll be able to actually draw conclusions based on it. Now, that's not to say that a fully connected network can't do image classification, because one of the most popular data sets for machine learning, which is in many people's mind the hello world to artificial neural networks and deep learning, is called the MNIST data set, which is a data set of poorly drawn, kind of poorly drawn, 28 by 28 numbers. And so what many people will do is they will take, what some people do, at least at first, is they will take all of these and just flatten them, as we talked about right here. And then at the end, we'll have a 784, we'll have 784 pixel long array, which we will then pass into our fully connected network. And then with the softmax function, as we had talked about before, this will give a probability about what it thinks the number is. Okay. Does that all make sense? And the same thing can be said about the recurrent neural networks. So if we have a recurrent neural network that looks kind of like this, and we have stock prices going in here from day 1, day 2, day 3, the beauty about these is that the data that comes in here plays not only off of this data, but it also knows the data from day before. And that will allow us to make more accurate predictions. That'll essentially allow us to take into account the memory of what would happen today, what happened this day. And this output also can be fed to a artificial neural network, multi-layer perceptron, and that can make like a MLP regressor, and that will be able to tell us what it thinks what it thinks the stock price might actually be. So in designing a network, it all depends on what exactly you are trying to accomplish. So just a regular multi-layer perceptron in most real-world scenarios isn't going to accomplish too much, but it all depends on what kind of data you actually have. So in the Boston housing data set, for example, what might be extremely useful is if we have the Boston housing data set from, in this case, I think it's like 1987 or something like that. If not, let's just pretend it is. And if we had the Boston housing data set from 1986 as well, and then we could feed it in through here, and we see how the price changes over time, as well as what data what data is taken into account from the previous year, and we'll be able to learn it from the next year. Now, to get back to a little more on point, because I feel like so many people are lost, as was previously stated. So we're going to step a little bit back into the math behind it, unless there are any other questions. Is there any other questions regarding all that? Okay.
Thank you.
So, and also, convolutional networks are best for like image processing tasks, but for convolutional neural networks, they're very, very, very computationally heavy, because for every single image we look at, we have to make an analysis on each of those 3 by 3. Back to when we had the image here, and we wanted to just grab like these pixels. We have to make an analysis on this. Then we have to make an analysis on these next pixels, and then we have to make an analysis on these next pixels, and just going to keep going through and keep going through and keep going through. And the part about machine learning that is nice about this is that it will slowly learn about which pixels it thinks are important. And that's how it'll actually learn, essentially. And it's not just like breaking images down into the simplest possible form. Does that make sense? Okay, so the connection between last class and this class, well, the neural networks are essentially another statistical technique. We did not talk about neural networks. We talked about like PCA. We talked about support vector machines. They're all just different machine learning techniques, essentially. So the previous, the support vector machines is essentially another machine learning way that we can do classification, for example. And then the neural networks is just a different way of being able to do our classification or our regression. So, as I mentioned before, the neural networks are really, really good for essentially describing any function that you really, really want to. Not any function, but for the most part. However, they tend to be more computationally expensive than the other techniques. So you could have a machine learning model, a MLP or different kind of model, running for up to like 24 hours before you're able to actually even use it. However, with a regression technique, you're usually just putting in all the numbers and you get a much, much, much quicker output. It doesn't always have high accuracy, as we see right here. So with our regression model, we got about 92% score. However, with this, it's about 80. And that's even after putting 2 layers of 10 and 20. So even though it just is not quite, it's not always more reliable, but sometimes it is essentially. So the beauty about something like scikit-learn and like sklearn is that the fluidity of being able to change your model almost immediately. Because I can just as easily put a linear regression model here, and then I can experiment to see which one performs better. So for many, many tasks, I would say use a much simpler method like regression model or even support vector machines, even though they can be, but they can be a little more complicated before even trying to use regression neural network. Yes. Yes.
So when I was like playing with this, I found myself sort of rerunning it. Is there some randomness built in, and it jumps around?
Yes.
Like you hit 79, 83. Like, is there some systematic way to sort of get a better kind of like some sort of formal result about the goodness of fit, like where you do some I don't know, like, but is there something to do other than just run it 10 times and average it in your head? Like,
Okay, so you absolutely can run it 10 times and average in your head, but you probably don't want to. When you were trying to rerun it, I assume you got probably about the same range, about?
yeah, I mean, it wasn't super tight though. It was like maybe a range of like 5 percentage points.
Okay. So sometimes it is all about getting lucky, because when we define the weights, we're still. When we define these weights, they're usually just completely random. And then it essentially will give your model a better place to work off of when you are trying to define it. And essentially you're doing a race and everybody starts at a different spot. And sometimes you start like right near the finish line, but sometimes you start all the way at the beginning. So you might have to maybe just train for longer to get a better fit. But essentially what will happen is that we will get a, let's say we have the function that we're trying to find looks a little bit like this. The entire, everything that we're trying to do, we're going to try to find this global minimum. So sometimes you might start like right here, sometimes you might start right here. And then when we get to this part right here, we're going to try to find the gradients. We're going to try to find the difference between where we're supposed to be and where we're supposed to find. We're trying to find the difference between where we want to be versus where we are. So even though we might see that this would be the ideal spot, the gradients won't be able to look very much far beyond this current place. And they would, in the simplest way possible, they would say, okay, it's impossible to get here, so we're just going to stay here. So that's essentially the randomness behind it, where if you start here, it's going to be a lot easier for you. If you start here, it's going to be a lot harder for you. Does that make sense?
Yeah, I mean, I get where the randomness comes in, and I guess the question is like, is there some like cross-validation or something you could do that will just like, if you want to answer the question like, is a 10,20 model sort of better than a 10,10,10 model? Is there some easy way to sort of do that, or do you have to just sort of run both and see which number's higher, and if they're close?
Normally, I would run both and see which one's better, for the most part. Honestly, probably 10,20 probably maybe should, like in my personal opinion, I would do 20,10, even though ignore what I did. Do as I say, how as I do, or whatever. But usually, when you have more layers, it's more complexity. And so what I like to do is I like to make it look more like a pyramid or a triangle and reduce the complexity as you go. And that way it'll be able to break down the more important features into simpler features, which will allow you to get to a better place. Because in that situation, we have something a little more akin to something like this. We have 10 and 20. And the output is essentially being told 20 different things as opposed to 10 different things. And it's just hard to make a better decision based on that. It's hard to learn based on that. So to actually answer your question, it's mostly within the experimentation behind it. You absolutely can average it out, but even if you were to do that, there's still going to be some degree of randomness to it. So there's really no best way to do it as opposed to training for more. You can add like more complex things like batch normalization and regularization to it as well. Okay. Any other questions? Somebody has to have a question. It's okay. So if we talk a little bit more about, if we talk a little bit more about the math behind all of it, we'll be able to talk about, so we can go back to our main equation, and then we, so essentially have our output to be something like this, and this will all be within a activation function. And then so on and so forth. They will each have their own activation function, which can be the Rayleigh function, the sigmoid, or another one is tanh, or hyperbolic tangent, where it's the exact same thing as sigmoid, except for it goes on a scale from 1 to -1. This will go from 1 to 0. So these will all be encased inside of one of these activation functions, and that will allow it to, as I said, add another layer of non-linearity to it in order to make a more robust prediction about what our model, or about what our function is supposed to look like. So we'll have, so we'll have all of our data passing through just like that. Now, on the other hand, we will have, when we're actually calculating the difference, we're going to use a loss function. Usually cross entropy. We're going to use a cross entropy function. Again, this looks like that. We're going to use a cross entropy function. We're going to have our labels, and we're going to compare it to what we have predicted. So as you can see here, this would be for a softmax function, the probability predictor. We have 7%, 70%, 2%, 1%, and we would pass it through essentially just the logarithm of our predicted and multiply with our the actual label. So the logarithm of 0.7 times 1, and we just sum all of this up. And then we will take the derivative of that, which will look very friendly to us. And it will essentially look like that. So we're going to take the derivative of the function that we got at the end of our cross entropy, pass it through this, and using this, we'll be able to identify how much different this is from the true label. So we'll be able to predict the difference. Well, not the difference, more of the derivative of what we actually want to calculate. And then from here, we're going to take the partial derivative of, we're going to take the derivative, so much that I didn't talk about. Just right now, I'm going to skip over the rest of these. This was from a previous class that we had done here, which just does all of this in the more basic mathematical forms. So essentially what we'll do is, at first we will declare our weights, the little lines here. We're going to set those random, as we can see here. Ready to, I feel like I'm losing so many more people than I'm holding. I should start over a little bit, right? No? Are you sure? Okay. So when we are constructing this, we construct the number of neurons. We construct our neurons. And then we construct the weights, because all of these have to be actually declared mathematically in code. So what we're going to do here is, I can also share this one if this will help more people as well. So we're going to find the input of our, we're going to find our input, and we're going to find our output. And we're going to declare the number of hidden units we want to use, how long our middle box is going to be. And then we're going to find the learning rate, and I'll discuss that in just a moment as well. When we declare our weights, we're going to make them absolutely random. And we're going to have them the size of our hidden unit times our output unit, or input unit. For the first set of weights, and this will be the hidden unit, we're going to make it this size by this size. And for W2, our these second weights, we're going to make it the size of our output times our input. This is going to be the input in this case. Yeah, and then the bias can just be 0. You don't want to have too much bias. So yeah, that's the reason that it's 0. There actually was a time when the weights were declared as 0, but that caused all kinds of problems, as anybody who's ever tried to multiply a number by 0 and try to get something other than 0 could tell you. And the reason that we have multiplied by 0.1 is just so we can have, like we're scaling it down, as we talked about before. Here's our sigmoid function. So it's 1 over 1 plus e to the negative x. I know this is really, really hard to see, but please just trust me that it looks like this for those who are having a hard time looking at this. Our sigmoid prime is going to be the sigmoid derivative. This was just talking about how we have the tanh function as well. We're pretty much going to use this as well. And so, when we actually pass everything through, we have Z1, which is going to be our first output. So we're going to have dot, which is dot product, multiplication of W1 and X, and plus our bias. And then we're going to pass that through our tanh function here. And we're going to get the output will be, we're going to pass the output of that through our W2, or to our Z2, so we're multiplying our W2, our second weight, so our second set of weights, multiplying it with our first output. And we're going to take the sigmoid of that in order to kind of squish it between 0 and 1. Because in this case, we're trying to find a probability. Okay, so I had previously said before that the softmax is best for probability, and that is still true. However, the sigmoid is still very good for probabilities if it's between two classes, binary classification. So in this case, we're going to predict the chance that we have a 1 as opposed to a 0, and then we're going to have greater than 50% of it being 1, greater than 50% is that it's going to be a 1, and less than 50% is going to be a 0. I'm going to outline the actual problem as well. This is all over the place. I'm very sorry, guys. So this is going to be our data set, where this is going to be one feature. This is going to be x1, and this is going to be x2. And the red and the blue are going to be different labels. They're going to be 0, and they're going to be 1. We're going to find the shape of it, so we're going to have 2 times 200, because we have 200 different data points, and there's 2 dimensions to it. In the Y shape, they're going to be actual labels, and we're going to have 1 or 0 behind each one of those as well. Talk about why we actually need to use the machine learning, applying the decision boundary. And if we just use a regular regression model, this will just be a straight line through. We're not going to be able to capture the complexity of this circle data, essentially, compared to the just a linear line. The accuracy is 50%, which is terrible. We can look at the predictions compared to the Ys. We can mainly pick out which one it thinks was a 0, which one it thinks was a 1. Here's a 0, here's a 1. They got this prediction wrong. Okay. Is there any questions? I know there has to be at least one, because this is completely out of the scope of our current course, but I just wanted to make the neural network part of it a little more, make it less like a black box, and also, take up the rest of the time that I had kind of flown through. Yes?
Just a quick question, I'm just trying to wrap my head around. So going back to the iris data set that
Yes.
we're talking about. So is your input layer, like the number of neurons that you would have, correspond each neuron to a feature?
Yes.
And then,
So in-
your output, I think we would have 3, right?
Yes, so
In
the
that
input,
case-
of the iris data set was like the sepal width, the sepal length, the petal width, the petal length. I think there were 5. I'm not sure. But we essentially have 5 neurons going down. We have the number of hidden, which could be 10, 20, your favorite number. And then this would be 3, and then we would find the probability for each 3. Any other questions? Okay. Now doing this with the neural network approach compared to the terrible regression 50% model that we just did, we're going to find the number of input x's with the number of y, the output. We're going to declare the horizontal box, essentially, and we're going to determine a learning rate. So the learning rate, we have an equation down here, is for when we're actually doing the learning behind it. So the learning rate will tell it how big of a step it wants to take. So what we certainly could do is we could have a function that we need to approximate. It looks like this. And if we have no learning rate, it's going to see that there's a very, very big delta between where we want to be versus where we're expected to be. And then, so we can so the idea is that we want to take a step in the right direction. So we might take a step this way, we might take a step this way, we might take a step this way. But if we have no learning rate, which is essentially just scaling it down, we can take a step over here, and then we're going to say, okay, we're completely far away from where we need to be, so let's now take a step over here, and then it'll just keep going in that direction. So the learning rate is essentially something that will just scale it down much, much smaller to a point where we can take very, very small incremental steps. The learning rate is something that also is a hyperparameter that you can tune that will also come kind of with the experience of trying to find the best one. It might be you have to just run the model 100 times and see, okay, learning rate of 0.01 was bad, we try it with 0.000. And usually when you have really, really bad accuracy, it means that your learning rate probably should be a little bit smaller, because it probably means that you're jumping around with this. Okay, so if we go back up, so we declared our segue function, our activation function, and our sigmoid prime, our derivative of our sigmoid function. So we're going to multiply these together, and then we're going to, run these, and this will essentially be what our output looks like. So our x's, which are just going to be very, very small like this. Our z1, which is going to be what we got when we first entered here, after we passed through the function, is going to just kind of look like this. Our a1 is going to be after the activation, and they're very, very similar. That's just because all of these are already between 0 and 1. Since we're passing it through the TNH function, it just makes a difference. Z2 is what we're going to have as our output, and then since this is 0.0, this is essentially 0.5. Right under 0.5, it'll predict it's a 0 because it thinks it's closer to 0 than it does to 1.
You go up in the equations, is every time you have an x, does that mean this is the input value?
Yeah, they're different input values. So,
But that's being applied to a data set, as in if we're feeding it, like x here is actually the x of the x we defined prior when we're actually feeding it.
yeah, so yeah, exactly. So the x is just one of these little dots. So if we think about this in the format that we're probably a little more used to in this class, it'll just be number 2 and then label. Where this would be an x, this entire thing would be an x, x1 and x2, which are different features, and this is our label.
And that's being repeatedly, like this thing is repeatedly feeding these x's.
Not in that
Label?
situation. Not in that
Yeah,
situation.
but this is like the one-time thing?
Yeah,
Is that what
this
you're-
is
okay.
one time thing. So we're just going through this, and then we're trying to predict it. Going through this, trying to predict it, and so on, and so on, and so on, and so on. Okay. Blah, 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 blah. This is the loss function that we used in this particular case. We don't have to get too much into it, but what this is perfect for binary classification, because the yi, which is going to be our true value, is going to be either a 1 or a 0, a 1 or a 0. And if it's a 0, it'll cancel out this whole term. If it's a 1, it'll be 1 minus 1, and then it'll multiply this whole thing by this term. So we're going to be able to find the probability of just one label. And we're taking our A2, which is our output value, at the point I, which is just one of these rows, and we're comparing it.
Is that just cross entropy for binary classification?
Yeah, it's just binary cross section. BCE. Yeah, binary cross section. And the cost is just going to, since we're adding all these up, the final cost is just going to be this divided by 200. That's just to get an average, because we're going to average out how well you want our model to do. We're trying to generalize it very, very much. So here is where we're going to actually perform the back propagation step, where we pass all of the data through, and now we just want to go back, and we just want to go back, essentially. So we can see here, this is actually wrong. This should be we need an additional layer of the cost function without something else completely overlooked. But we need to use the sigmoid prime, essentially. And then we're going to, we need to update the weights, because the weights are where the magic actually happens, because we're just passing numbers through, and using these weights, they're going to pretty much tell us how much we want to, how much each number is important. In this case, they're both pretty important because their data set is essentially just classification of where something is in the map. So we're going to do the multiplication with our A1, which is going to be essentially the output from this step right here, or I guess this step right here. And we're going to multiply that with the DC2 difference. DB2 is pretty much going to be the same thing, although it's sum because our equation looks. So we're doing the dot product at the W or M because we're doing a multiplication here, and then we're doing a sum because the bias is a sum. And we're just going to go back through. This is actually the derivative of the tan h function, the function that looks like this. This is just written down the derivative of the tan h function, and that's because we need to take the derivative of that as well as we should have with the sigmoid. We should have done with sigmoid prime. And we're at this point right now, and then we want to update these weights. So we're going to multiply it by the initial input, multiply it with our derivative of C1, which is that after it was calculated. Same thing with B1. Now finally, we're actually going to update the weights by multiplying the initial weight with the difference with our learning rate. Our learning rate, as we're going to call it, is how big we want our step to be. Essentially. Okay. So we just did a forward propagation, what it's called, and a back propagation, what it's called. So if we want to automate that, we're going to need to run it like 1,000 times, as we had said before. So we're going to declare some functions just because it's a little bit easier to use this way. So here we're just doing all the exact same stuff as we did up here. And we're just going to store all of these in a dictionary of parameters that we can use later. Same thing with the forward pass. We need to grab our parameters. Because we need to obviously do multiplication with it. So we need to grab our parameters. So we're going to pass our parameters through here, multiply it all together as we did up above, and then we're going to return this. Same thing as here essentially. We're just taking our C1, A1, C2, A2, and putting it in there. So we're returning the A2, which is going to be our actual prediction, and the cache. This is inefficient because we can just return the cache and then scrap the A2, but oversight. And here's just going to be our cross entropy function. GPU cost is going to be cross entropy, as we had talked about right here. Here's our backward propagation. We're going to use our W's and our A's, our weights and our activated inputs. We're going to do all of our back propagation, and then we're going to get our gradients. And then here, all the exact same stuff, just grabbing our weights, grabbing our differences, or deltas, derivatives, whatever you want to call them, and we're just doing the parameter update as we had previously done. And here we're going to actually put it all together, where we're going to make a full model. We're going to pass in our inputs, the number of hidden neurons we want, our Y, our outputs, the number of iterations, so like that 1,000, we can make it 10,000, 100,000, 5, 10, whatever you want. And this is just doing the request. So we're just putting this all together from when we initially grabbed our inputs and outputs. We're going to initialize all of the parameters with the numbers that we want. the number that we have, the hidden and the output. We're going to grab all of our parameters here, and then in range iters, that just means we're going to loop over it iters number of times. We're just going to do a forward pass, compute the cost of it, do a backward pass, and then update all the parameters. And then if it's like divisible by I and it's 0, we're just going to print the cost. And here's just an actual picture. So then we can call our pool model, where our x is our x, our hidden is 7, our y is our y, our outputs, iters is 50,000, and print cost is true. And then we can see what we want is that our cost is slowly going down because the cost is just a fancy way of saying how bad our model is doing. And we want our model to do the least bad as possible in simplest terms. Then we can plot it, and then we can see that we do a lot better than the 50%. And so oh my god, it's 100% accuracy. So something that's very, very interesting about this case is that if you have 100% accuracy, you have a bad model, because that means your model is most likely overfitting. So what we want to do is we want to generalize our model as best as possible. We don't want to make the perfect model every time, because that will, it means we're overfitting to our training data. That means that it's going to be very, very bad for outside data. If we can guarantee that our data is going to come from a similar distribution as this, it's probably fine. But otherwise, if you have one red dot that's right here, it's going to be predicted as blue. And if we have all the, like a whole bunch of red dots that are just on the outskirt, it's going to be predicted incorrectly. So yeah, looking back on it, I probably should have added a little bit more noise in here where more blue dots would spawn here, but also hindsight. But this wasn't always, actually, what did I do here? Okay, so here is a essentially a completely new data set where we actually have some red dots spawning outside here, and then we are effectively missing these predictions, which is going to tell us that we are at 93%. And, oh yeah. And so, a way we can tell if our models are overfitting, I think this was more fun than anything. So we can run our exact same model on a data set that looks like this, like a cool flower looking thing. And it's going to do really, really, really bad because it doesn't account for all of these interesting flower looking things. So if you had a data set that was a combination of this, the flower looking things, and the circle, our model would learn something completely different and be able to map out everything a little bit better for the most part. So we can run the model again, and we can actually find this better. So I'm sorry I had to like fly through that notebook. That was initially for a 2-hour class where we had many, many questions and many, many.
Remember that was still with the 7 hidden units?
Actually, I don't even know. Yeah, that was with 7. But it shows that our with the 7 hidden units, we're able to still find complexities like this.
How do you prove it? Why the second one's better than the first one? Where did you change?
Oh, so what happened was we pretty much just created an entirely new model. And then we made predictions, and we ended up here. In this situation, we again did not split between training and testing. So what would have been better is if we had actually split it, and we would be able to make a little bit better predictions. We'd be able to get a better real-world example of how well our model would do compared to data from the same distribution, data that the model would actually see compared to this. Any other questions?
Can you go back up to where it fitted really bad? where the flower is.
Oh.
Little flower thing, so it was pretty bad up here.
Yes.
And it's reporting to 200% accuracy.
Yeah, and that's mostly because like 50% of the dots are out here, I guess. And they're like it's getting some right here. It's getting some right from the red in here. But I think that just because there's a pretty decent distribution within here, where I assume that I personally did not count the number of dots in each one. So yes, but I assume that like let's say 100 are in here, and then another 100 are out here. It's predicting all of these other 100 blue ones, or let's say 50 blue ones, that's correct, and the 50 blue ones that are in here is incorrect. Whereas in here it's correcting, doing the 50 red ones in here are correct, and the 50 red ones out here are incorrect.
So, but from that point to the next point, how did the model differ?
Because what we did was we just retrained it on this new data distribution.
Oh, okay.
Yeah. I kind of like waved
Where's that?
I kind of waved my hand over that and said it's magic. But so we had grabbed all of our data.
Oh, this stuff?
Yeah, we grabbed all of our data from here, and then essentially put it here, plotted all the boundaries, made our predictions, and now we're going to repredict it with the new data.
What's the predict function?
Predict? Oh, the predict is actually making the predictions based on, it's passing all of the x's back, it's passing all of the x's back through. Again, did not separate. What this is doing is it's taking the A2 cache, our actual prediction, and the like the whole list, passing forwardly, passing it, and then if the prediction that if the A2 is greater than 50, it's going to return a 1. If it's less than 50, it's going to return a 0.
So the back.
We're not doing back propagation here. We're just making actual predictions because we don't need to do back propagation if we're actually predicting a model. Because right here is what we're looking for the most part. We're looking for whatever's right here. So when we're actually making a prediction, we just pass all of our data through, and we send it through as if we don't have any true labels. You have a question?
In terms of accuracy for the neural models, if I get say an accuracy of say like 99%, what are the parameters that I need to check to make sure that's the best accuracy this model can do?
So that all depends on your problem. Because if you're trying to predict very, okay, so let me rephrase. So what I've always done is I've thought of if I make a model, I say, okay, how good can a human do on this particular case? For example, I saw there's an Israeli company that essentially just looks for data within a legal document, and their model predicts, has like a 94% accuracy of being able to find the correct information. And then people said, okay, so how, is that good or is that bad? So what they did was they took actual lawyers, gave them the exact same document, and those lawyers were only able to find 86% of the stuff correctly. And what took them 2 hours took the model like 1 minute. So it's mostly based on how well a human can do. What you need to do to get the best accuracy is the weights are what is essentially the magic. So you want to log the best weights in a way like a pickle file, which essentially just lets you store like more complex things, lets you store complex data, and just reapply all those weights. And then what people might actually do is for even more complex models is the cost function will not always go down. It'll sometimes like jump around, and most of the time cost functions, ideally they look like this, but 99% of the time they look like this. And so you still see that curve, but you still want to get like the one that's about right here at the best accuracy possible. So at this point, you would want to essentially make a note of what it thinks is the best, what is the best accuracy there. As far as actually doing you might want to do more hyperparameter tuning, which is increase the learning rate, decrease the learning rate, use different optimizers, which is something we didn't really talk about today. But there are pretty much a multitude of different things that you can adjust. You can use regularization, weight decay, a little bit out of the scope of 1 minute. I would mostly say, do trial and error. Think about how well a human can do at the task. Because if you want to do a classification task, and you want to classify shirts from pants, a human can do that very easily, so you would want your model to do that pretty easily. But if your model is predicting all the shirts as pants and all the pants as shirts, then you're using it. Does that make sense? Any other questions?
That's good. Are we going to be talking in this class next class about the automated machine learning?
We will not talk about auto ML. That's a bit out of the scope of this class, especially. I don't even think we were supposed to get into this, honestly. I was not expecting that. We will not really get into auto ML. There are a lot of really, really good papers out there, which we can discuss if you would like, that you can look at.
Just to get started.
What's that?
Just to get some idea.
Yeah. So, yeah.
So what would be the next class?
Oh, that's right. So, the next class. Oh no, this is the wrong notebook. The next class, I'm leaving it mostly up to you guys. There's a straw poll here at the very bottom of the meetup screen. Running next class, we can learn more about the math of neural networks, which would essentially be what we talk about here, but we can actually talk about some of those more advanced things like the different optimizers, your different like regularizations, et cetera, like more stuff to improve your network better. Introduction to deep learning frameworks. We can talk about TensorFlow, PyTorch, and Keras. Pretty much just throw a model together with that, because with scikit-learn, it's not very, very good for the very, very deep models. So we had examples where we had like 3 layers, but sometimes you need 100 layers, for example. And we get more into frameworks that will let you do this a little bit better. Or we can talk about decision trees, solid models with random forest classifiers, where the reason I was a little hesitant in doing this is because Machine Learning 101, I know, covered these. However, random forest classifiers are still probably probably the best possible classifier you can get without doing like the intense machine learning, where it'll be very, very fast, it'll be very, very accurate, and you don't have to go crazy with all of your data quite as much. So I'm letting you guys decide. I'll probably post in the meetup on what it will actually be, or I mean, you can even push on the results button. I'm also deducting 1 from here because I voted for this once, and I was just testing to make sure it worked. So whatever this is, it's this -1. So does anybody have any other questions? Or if not, we can log after class because it is 2 minutes over. Otherwise, thank you for coming. Thank you for sticking around, even though I had prepared the shortest notebook in the world and then covered using that. I will post the other notebook as well. I think it's already out somewhere. So yeah, other than that, I hope you guys have a great night.